Hello everyone, today we are finishing our 2D geometry unit with our section 5 covering geometric probability.
Probability is most easily calculated as a fraction. If you think back in your minds, you might remember learning that probability gives you this fraction where we have the total number of events on top. And on the bottom, previously you might have heard number of possible outcomes. That's the same as saying the sample space. So number of events being what you're looking for, sample space being where it's coming from. So, for example, the probability of flipping a head on a coin, well, the coin has two sides on it, heads and tails. So your sample space is 2, but there's only one head, so there's only one chance of a head, so that's the event is 1. The probability of rolling a 1 or 2 on a 6-sided die. Okay, well, there's 6 sides, so your sample space is 6. It says 1 or a 2. Or implies that it could be one or the other. So I would win on either of those 2 times that it lands on a 1 or a 2. So, or in probability, another way you might think about it is kind of like saying you're adding. So there's a chance of a 1, a chance of a 2, 1 plus 1 is equal to 2. The probability of randomly selecting a freshman in our class. Okay, so we're doing remote learning. We can't really figure out exactly how many freshmen are in each individual class. So let's just say there's 24 people in our class, so that will be our sample space. And let's say that 3 of them are freshmen, so there's 3 chances of selecting a freshman out of the total 24 students. All right, let's look at a few different ways to calculate geometric probability. So we have the length model here where we have the sample space of all points from A to D and all points on our red B to C is our event. So the probability is taking the event and putting it on top of the sample space. So all events are going to be the numerator of a fraction. And let's fix that, numerator. And all sample spaces will be the denominator. So if we're looking at angle measure, the total sample space is the entire circle all the way around, but the event is just the shaded region. So you have your event, measure of the shaded region, over the sample space, which is 360 degrees because it covers the whole circle. Then we have area, where it says that we have, for a sample space, all points inside the rectangle, that's all the way around, that includes the triangle. And then it says the event is the points inside the triangle, so you have to do the area of the triangle divided by the area of the rectangle. All right, let's look at a few examples. Example 1. A point is randomly chosen on the line segment PS. Find the probability of each event below. Okay, so before we do anything, the sample space is the whole line, and we have 7, 13, and 5. So we need to add those together to find the total length of PS. So I have 7 and 5, and we're adding those to 13. We're going to squeeze that on top up there. 7 plus 3 is 10, plus 5 is 15. Carry the 1. So that gives me 25. So PS is equal to 25. That's my total sample space. So right away, I know that all of these fractions are going to have 25 as our denominator because the sample space goes on the bottom of the fraction. All right, the point is on QR. Well, the distance from Q to R is marked as 13. So that means our probability is 13 out of the total sample space of 25. The next one says the point is on RS or PQ. Now remember we said that that word or kind of means addition, so it could land on PQ or it could land on RS. Either way, we still win. So I have 7 plus 5 is equal to 12. So my probability is the 12 times that I could win out of the total 25. All right, and this last one is tricky. It says the point is not on PQ. That means that it could be on QR or RS. So it is on QR or RS. QR is 13. RS is 5. 13 plus 5 is 18. So the total probability is 18 out of 25. Example 2. A point is randomly chosen in the rectangle below. What is the probability that the point selected is in the circle? Okay, so we are working with area for this geometric probability model. Because the total sample space is the rectangle, I need to find the area of the rectangle. So area of the rectangle, and I'm gonna shorten this a little bit by drawing a rectangle down here. That's not proper notation, so don't actually do that. All right, so area of a rectangle, base times height, I have 12 times 4. The total of that, 12 times 4, is equal to 48. All right, so I have my rectangle. Now it says the probability that the point selected is inside the circle. So I don't have to worry about that triangle over there. I'm just going straight to the circle. I know because the circle is the exact same height as the rectangle that the diameter is equal to 4 inches. So if I want specifically the radius, I have to divide the diameter by 2, so the radius is equal to 2. 4 divided by 2 is equal to 2. So now I can go ahead and find the area of my circle. Area of the circle is equal to pi times the radius, which I found to be 2, squared. 2 squared is equal to 4, so I have 4 times pi, which when I calculate that out, 4 times pi, and I did use the pi symbol on my calculator, 4 times pi is about equal to 12.57. All right, so now I can take those two numbers and I can put them in my fraction. So I have the number of events occurring is 12.57 over 48, which is the total sample space. Now, in general, you don't really want to leave a decimal on top of a fraction, so the best thing you can do here is multiply both the top of the fraction and the bottom of the fraction by 100, and that's going to get that decimal out of there. So I have 1,257 on top and 4,800 on the bottom. And if you're interested in simplifying this fraction, which with probability you don't always have to, but sometimes it does make things easier. So if you are simplifying, I'll go ahead and cut to the simplified answer for you here. You should end up with 419 over 1,600. So that would be your simplified version. All right, example 3. Example 3 says, a point is randomly chosen on the dartboard below. What is the probability that the point is on the second ring? Okay, so regardless of if you start in the center and call this ring 1 and go out, or start on the outside, ring 2 is always going to be that blue ring. So I need to figure out the area of just the blue ring. But because we're looking at probability, I need the total area to be my sample space. So I'm going to start with finding the total area. So total area, we have a radius of 2 plus 1 plus 1. So I have a radius of 4. And to find that, I'm going to say that this is area of T for total. That is equal to pi times the radius, which is 4, squared. So this is equal to 16 pi. Because all of these are going to be circles, I'm going to keep them in terms of pi so that when I do have my probability, I can cancel my pi out. You'll see what happens with that when we get to that point. All right, so I have my total area. That's my sample space. Now I need to find my chances of the event happening. So that's where I need to find the area of just the blue ring. When you're using the area of a circle, you're covering all of it though. So we have to find both the area of the circle surrounded by the blue ring and the interior circle, that ring 1, so that we can cut it out. So I'm going to go ahead and say that this next piece is area of ring number 2, and the radius for the whole thing is equal to 3. So I have area for the blue outlined circle is equal to pi times the radius, which is 3, squared. So I have 9 pi. And then I have to do that again to cut out that centerpiece. That centerpiece has a radius, I'm going to say radius of the center is equal to 2. So I have area of the center is equal to pi times 2 squared. So I have 2 squared is equal to 4, so I have 4 pi. All right, so now I have all the pieces of information I need. I'll circle those real quick. So in order to find the probability of just the blue part, I do need to do my subtraction where I'm subtracting the area of this entire circle. I'm cutting out the center. So I have my total area for that circle of 9 pi, and I'm going to subtract the center of 4 pi, and that leaves me with 5 pi. So my probability is going to be, the probability of landing on the second ring is 5 pi over my total area of 16 pi. Now I mentioned before that the pi's are going to cancel out, and they do. So that means that the probability of the point landing on the second ring is 5/16. So that's where that 5/16 is coming from there. And this whole sentence is my answer.
This is where we're going to end our unit. We will continue with Unit 11 covering 3D geometry.